In this video, we're going to go ahead and actually get the player to be moving around in our scene with the camera following it. So that means we're going to be fleshing out our player script that we created in the first video. If you didn't follow along with that video, all we effectively did was create the code folder and placed a player into it. It doesn't have any actual behavior inside of it, it's just the default Unity mono behavior template. So the first step is the way that we're going to organize the logic for our player is to separate it out into multiple classes. We do this so that we maintain some level of organization. We try to stuff all the code that we need inside of our player controller into a single class. We would result in code that's very difficult to see the organization of or to modify in the future. So I'm just going to show a really straightforward organizational strategy that we can do to accomplish this by making use of additional classes that aren't necessarily mono behaviors. However, that will bring in some interesting concerns that we'll deal with here in a moment. So the first thing I'm going to do is I'm going to delete everything inside of our player class that was given to us by the template. The next thing I'm going to do is I will be placing the player class inside of a namespace. Fortunately, newer versions of Unity do support this feature. So I'm simply going to say namespace assets.code. Doing that, not arbitrarily, as you can see over here, the way the project is organized within Visual Studio, we have an assets folder and a code folder. So that's why it's going to that namespace. Now our player mono behavior, like I said, is going to be made of multiple classes. So let's go ahead and create both those class files, and then I'll show you guys how to hook them up, and then we'll fill them out with logic. So the first class I'm going to create is going to be called the player controller. Now the player controller is simply going to be a normal .NET class. However, it still needs to be able to modify the player in some way. Well, obviously the player controller is responsible for movement that is calculated based off the input of the mouse and the keyboard. So we need to be able to reference back to the player mono behavior in some way. The easiest way to do that is simply to create a constructor that accepts a player class as a parameter. I'm going to call it player. Then I'm simply going to assign it to a private read-only player field on our player controller. Now the next thing I'm going to do is I'm going to create a method on our player controller called update. Now it's important to understand that because player controller itself is not a mono behavior, this update method is not going to be invoked automatically by Unity. We'll have to do an extra step within our player mono behavior for this method to be invoked, but we'll worry about that here in a moment. For now, just understand that what we just made is a method that's public, and it doesn't in any way tie back into the Unity game engine whatsoever. The next thing I'm going to do is I'm going to create the player camera class. Now the player camera class is going to control the movement of the camera as it follows behind the player, which means that it will need a constructor because it will need to reference back to both the camera that it's responsible for as well as the player it's responsible for. So I simply have to pass in two parameters, one for the player and one for the camera. Now, you'll notice that the camera is red, and that's because I haven't imported the Unity namespace. So I'm going to simply do that, and what we get up here on line 1 is a using Unity engine. That's going to allow us to reference all the built-in Unity types.
Is that since Unity 4? Because that's really awesome that they've done that.
Well, I mean, since when writing in C# we have to reference the Unity engine class because that's where all the types live. You might not have noticed it before when creating mono behaviors because the default mono behavior template includes it automatically. So
gotcha.
it's a step that's required for people who create classes that aren't created from the Unity editor itself.
Okay.
So now that I've done that, I'm going to assign both player and camera to local fields, private read-only player, and private read-only camera. And I'm also going to create a public void update method. Now remember, the public void update method is not magically invoked by Unity because it's something we're going to have to tie in manually. But now that we've stubbed out both our camera and our controller, I can go ahead and plug them in to our player class. And our player class, remember, is a mono behavior that will indeed be attached to our player game object. Now, you'll notice that in the player camera, I accepted a reference to a camera. Now, that's because I like to be explicit about what camera I'm dealing with, because in Unity, you can have multiple cameras in a scene, and that technique is actually going to be very useful in later series when we put together our radar. But for now, since we only have one camera, it might seem a little silly why we aren't using camera.main or something to that effect, but I find that being more explicit is typically better. So if we go back to player, we need some way for Unity to pass in the camera that we want to use for our player camera class. To do that, I'm going to create a public camera field that will allow us in the Unity editor to select which camera we want to be associated with the player. The next thing I have to do is I have to create two private references, one to my player camera, called camera, and one to my player controller, called controller. Now, these two references will hold references to the objects we're about to instantiate of type player camera and player controller. But we need to instantiate them. How do we do that? Well, since we can't create constructors and monobehaviors due to the nature of how the monobehaviors are implemented in Unity, we instead take advantage of the public void awake method. Now, since this is a monobehavior, the awake method is indeed invoked automatically by Unity. In fact, awake is invoked when the component itself is attached to a game object, which makes it the ideal place to instantiate our two subcomponents, camera and controller. So let's go ahead and do that. We instantiate camera simply by saying camera equals new player camera, passing in a reference to player and passing in the reference to the camera that we want to follow the player. So for the reference to the player, we'll pass in this, and to the reference to the camera, we'll pass in camera. Again, that is how we are passing the information to our player camera that will be used to update the camera based off the position and orientation of our player game object. Next up, we have to give the same treatment to our controller, so I'll simply say controller equals new player controller, passing in this as the parameter of our player, again, which allows our player controller object to reference the correct game object in our scene. Now, the final thing I'm going to do in player for now is, again, if you recall, the update methods we wrote in player controller and player camera, since they aren't tied into Unity at all, we have to actually be a little bit more explicit about how they're invoked. It's actually very easy to do, because I can simply say public void update, and I can say controller.update and camera.update.
And it's important that you get controller in there first because the camera is essentially following what the controller is doing, right?
Exactly. Since the controller itself is going to update the position and orientation of the player game object, we want to make sure that the camera is always following the latest coordinates of that game object. So that's why order in this case does matter.
Awesome.
So again, this might seem a little silly at first that we're basically doing more work to separate our code out into 3 different files. But in reality, once you start to work with the different bits of code that constitute a cohesive player component, it becomes important to separate that stuff out so that, well, things don't get jumbled and confused and annoying.
Now, aside from being much better in terms of being able to tell what's going on, does separating that give you more control over what you want to do too, or is it really more just about organization?
It's all about organization, and organization in code is incredibly important. You should always be able to answer the question, where should this code go? Code should always have a home. When code doesn't have a home, you end up with monolithic monobehaviors that are thousands of lines long, and it becomes nearly impossible to edit them in any way that doesn't inadvertently edit something else that you weren't intending it to.
So that's really important, even if you're working by yourself, let alone in a team environment where somebody may need to understand what you did.
Right. And remember, in 6 months, you won't even understand what you did. So it's important to always code for yourself in the future, even if you're not in a team.
Gotcha.
So just to recap, our player class is a monobehavior, and his update method, which is invoked by Unity automatically, will delegate to his 2 subcomponents, our controller and our camera. Okay, so the way that I'm going to put these classes together is going to be kind of staggered. I'm going to put together the bare minimum in my player controller to get him moving around with his velocity and his rotation. Then I'm going to write the player camera script so that the camera properly follows along with the player. Then I'm going to go back into the player controller and flesh out the rest of it. So I'm doing that because the camera, the way the camera is oriented, really will impact the way the player moves. So you kind of can't do one without the other. So I'm going to jump into player controller, and I'm going to start off with creating some data, because we're going to need quite a bit of little bits of information to track the velocity of a player, as well as the constraints that velocity may have. If you recall from the intro video, the player actually always moves along with a constant base speed, but that base speed can be modified by a variable speed that is inputted by the keyboard. So to that effect, I'm going to go ahead and create a couple private floats to track the velocity of our player. The first one is going to be base velocity. The base velocity is the current minimum velocity that the player is going. Then I'm going to do target velocity. Target velocity is going to be used to interpolate between his current velocity and his target velocity so that we get a smooth transition from going slow to going fast. Then we have our variable velocity. Now, variable velocity is used to determine how much the user has pressed W or S in order to affect the velocity of the player. Next up, I'm going to create some public properties. Now, the reason why I'm making these public, well, there's two reasons. First of all, other components within our player controller, or other components in addition to our player controller, are going to have to be able to access this information to properly work. For example, the GUI component that we'll eventually be writing is going to have to know where the player thinks the current mouse position is to draw crosshairs, in addition to knowing its current velocity and all that fun stuff. In addition, I like to leave these as public properties so that we can actually modify the behavior of our player during the game, despite the fact we will be providing default values inside of this class. So the first thing I need is my public vector3 mouse position. Now, why am I storing the mouse position in an additional variable as opposed to using input.mousePosition? Well, the answer is there are going to be two different movement methods for our player controller. One that uses relative positioning and one that uses absolute positioning. The reason I do this is due to a deficiency inside of the Unity editor for dealing with locking the cursor into the center of the screen. We'll see an example of that later down the road. So in order to handle the ability to move relatively and absolutely, I'm aliasing out our current position into this variable so that we can change that behavior with only a couple of lines of code. You'll also notice that, as I had to do in the player camera, I will also need to import Unity Engine by adding a using Unity Engine line at the top of my file. Finally, I will make this a private set. The reason I'm doing a private set is because I don't want anybody else to edit the mouse position other than the player controller itself. Next up, I need a way to track my current velocity, which you'll notice is stored in the float. And the assumption I'm making is that the player's velocity is always how many units per second he is moving in the positive z-axis. So that's why I can represent it as a float and not as a vector3. Again, we're going for a very arcadey feel for our controller and not a particularly realistic one. Next up, I need the max variable velocity. And of course, I got the get set mixed up. Or no, this needs to be private set because I don't want anybody but the player controller to be modifying the current velocity. But the max variable velocity is modifiable outside of the component so that we can change the behavior during the execution of the game. Now, the max variable velocity is the amount that the player can choose using the keyboard to increase or decrease his velocity on top of the base velocity. Next up, we need our minimum velocity. The minimum velocity is the minimum velocity that the player is always going to be moving at any given time, which again, as you saw in the introduction video, adds an additional level of difficulty into the game.
Check velocity on there.
Okay, next up, well, thanks. Next up, we need acceleration. Acceleration is a modifier that will be used acceleration is the modifier that changes how quickly our variable velocity changes based off of us pressing the W or the S keys. Next up, we need our velocity damp. Our velocity dampening is going to be used to determine our current, or not our current, but determine how quickly we move our current velocity to our target velocity through lerping or interpolation. Next up, we need our rotation speed. Rotation speed will determine how quickly the player rotates depending on where the mouse is positioned. Next up, we'll need a public boolean for use relative movement. Our use relative movement will determine if we're using relative movement with our mouse or absolute movement. We'll see an example of why I have this flag in very shortly here. And then finally, if we are using relative movement, we need sensitivity. Close enough?
Close enough.
All right. So if we're using relative movement, we want to know, like, if we move the mouse X amount of pixels, what that should translate to as far as moving the virtual mouse cursor, if you want to call it that. Okay, so now that I have all of this data all set up, I want to provide a lot of defaults inside of our constructor. Although most of these things are overwritable, we do need to default it to something sane. And I have a lot of numbers chosen out already, which we might play with in a future video. The first one is max variable velocity, which is going to be 20. So 20 units per second is the maximum amount the user can choose to go forward, or he can choose to have a variable velocity of 0, which means the player will be always moving at minimum velocity. Next up, we need our acceleration, which I'll do to 70. Next, we have our velocity dampening, which I'll set to 20. Then our rotation speed, which I'll set to 0.03 f. Now the f is important because rotation speed is a float, and 0.3 in C# is a double literal, so I need to add the f modifier to it so that it turns into a float constant. Next up, we need our mouse sensitivity, which I've already chosen to be 700/700. We can adjust that to whatever we want. And then finally, use relative movement, which will be set to false. Now, another interesting thing to note about these variables is just by changing these variables, we can significantly alter the feel of our ship, allowing us to use this player controller through a variety of different ships in the game that all have drastically different feels. So that's one of the reasons why I liked having placed all of these different things into public properties that can be modified to whatever suits your needs. So now that we've done that, we now need to write our update method. Our update method is going to be responsible for basically one thing, and then it's going to delegate to two other methods for purposes of cleanliness. The one thing that our update method is going to be responsible for is locking our cursor if we're using relative movement, and setting our mouse position depending on whether we use relative movement or not. So what I'm going to say screen.lock cursor equals use relative movement. Now this will come into play. You'll see an example of why I did this very shortly here. Next up, I need to say if use relative movement, then we actually we modify our mouse position based off the relative axes that were changed during the last update call. What do I mean by that? Well, I simply mean mouse position plus equals new vector 3, passing in input get axis mouse x times time.delta time times mouse sensitivity.x. The y-coordinate for this vector will simply be input.getAxis mouse y times time.delta time times mouse sensitivity.y. So that's in essence what I mean by using relative positioning. We are moving the mouse cursor relative to our mouse sensitivity and how far the mouse was moved in the last frame. However, if we're not using relative movement, then we simply say mouse position equals input mouse position, and everything's just fine, because at this point we're using absolute positioning, where our mouse position is determined to be exactly where the mouse cursor is on the screen. Finally, we're going to delegate off into two methods. We're going to delegate off to update position and update rotation. I made these two methods to simply clean up our code a little bit so that we're not mixing our rotation calculations with our position calculations.
Alrighty.
Okay, so now I'm simply going to write a private void update position and a private void update rotation. So these are our two method stubs that we will be filling out. Now again, we're not doing everything in our player controller quite yet. We still have our afterburner to deal with. We still have strafing to deal with and all that fun stuff. But for now, we're going to get just enough out of the way so that we can work on our camera. The update position method is responsible simply for moving the player along the positive z-axis relative to itself. So it needs to calculate the current velocity, it needs to interpolate between the target and current velocity, and then it needs to actually translate the player. So to do that, I'm simply going to say variable velocity equals mathf.clamp. Now, what am I going to pass in mathf.clamp? Well, I'm going to pass in variable velocity plus input.getAxis vertical. And then I'm going to multiply that by time.delta time. Then I'm going to multiply that by acceleration. The second argument I'm passing into mathf.clamp is 0 for the minimum. And the final argument I'm passing in is max variable velocity. Now, mathf.clamp is a fun little utility function that will clamp whatever this argument is to a minimum of this argument and a maximum of this argument. So if we try to go lower than 0, it'll just simply return 0. If we try to go higher than max variable velocity, it'll return max variable velocity. The calculation we're performing is simply adding the result of multiplying the vertical axis by the time between frames by our acceleration modifier. Now, the vertical axis is by default going to be accessed through the W and S keys on our keyboard or through a game controller, depending on what we have plugged in.
Sweet.
Now that we've done that, let's calculate our target velocity. Our target velocity is always going to be our variable velocity plus our minimum velocity. Remember, our minimum velocity is going to be the minimum speed that the player is moving, which adds in the level of difficulty into the game, because navigating a asteroid field when you're going really fast isn't as easy as navigating one when you're going slow. Next up, I need to interpolate between my current velocity and my target velocity. I do this so our player has a sort of semblance of gaining speed. Even if we jumped from a target velocity from 20 to 40 in one frame, we still want the current velocity to slowly ramp up to that target velocity. So to do that, I'm simply going to say current velocity equals mathf.lerp from our current velocity to our target velocity. Now, the t parameter that we pass in is going to be a function of time.delta time multiplied by some sort of dampening factor, which I'm going to pass in velocity damp. Remember, velocity damp is going to be the speed that our velocity changes. So a smaller velocity damp will result in our player accelerating slower, whereas a higher velocity damp will result in our player accelerating quicker.
Okie dokie.
Now that I've done that, the last thing we need to do in this case is to translate our player. So I'm simply going to say player transform translate, and I'm going to pass in 3 arguments. The first argument is going to be how I want to translate in the x-axis, which is going to be 0 for now. The next one is going to be the y-axis, which is going to be 0 for now. Then the final one is the z-axis. Remember how I want the player to be considered moving forward if he's moving along the positive z-axis. So to do that, I simply need to say current velocity times time.delta time. I will be passing in one more parameter or argument into this method, and that's space relative to. I'm going to pass in space.self. That means that he's not going to be moving forward in the global or the world positive z-axis. He's going to be moving forward in his local positive z-axis, which will make it so that he's always seems like he's moving forward no matter what his current rotation is.
That makes sense. Otherwise, in the game, he could literally only go forward in space.
Right, which would be problematic. Okay, the next method that I need to implement is my update rotation method. And that method, not surprisingly, is going to update our rotation. We're going to fill out a little bit more of this in a moment, or after we get back from playing with our camera. So I'm just going to put in the base bits in here, which is simply going to say mouse movement equals. Then I'm going to say mouse position minus new vector3 screen.width divided by 2 f screen.height divided by 2f, and then I'm going to multiply all of this by 0.2f. Now what this gives us is it gives us the it basically, I guess you could say it's center. Well, first of all, it gives us a point that is centered in the screen, and then it subtracts that from our current mouse position, which gives us an amount of pixels that the mouse cursor is away from the center of the screen, which actually allows us to take this information and pass it directly into a rotate method.
Now, is this part of dealing with the fact that Unity is not good at locking to the center of the screen?
No, in this case, this is the calculation we need to perform because we need to know if the player is moved if the mouse cursor is to the right of the screen, we want to rotate him to the right. If the mouse cursor is to the left of the screen, we want to rotate to the left.
Oh, gotcha.
And the further away from the center of the screen it is, the more we want to.
Then the harder he's going to bank.
Yep.
Gotcha.
Next up, I'm going to implement a small dead zone. I'm going to say if mouse movement dot square magnitude is greater or equal to 1. So that means we're only going to perform this operation if it's past a specific dead zone, which allows us to kind of have our mouse not necessarily directly in the center of the screen without the player moving. So it makes it a little easier to rotate things.
Yeah, gives you a little play in the mouse.
Yeah. And you can modify this variable to whatever you want, of course. Then I'm going to say player transform rotate new, vector3. I'm going to pass in negative mouse movement y, mouse movement x, 0 times rotation speed. Now I have to invert the mouse movement y because by default the mouse position, the way this calculation needs to work is it needs to work with the y coordinate going in a particular direction, but the way that the mouse position itself works is the y coordinate going in another direction. It's just the difference between screen space and world space. So we have to compensate for that by negating the mouse movement.y. Okay,
Alrighty.
So this is actually the bare minimum we need to do in order to get our player controller to actually control the player to an extent. So now let's jump back into Unity and attach my player mono behavior to my player game object. Now remember, I'm not attaching my player camera and my player controller classes to it because they aren't mono behaviors. They're just used internally by the player mono behavior to perform its calculations. So let's go ahead and click and drag player onto my inspector while I have my player game object selected. And then let's click and drag my main camera onto my camera so that the player knows what camera is associated with. And then let's hit play. So this doesn't quite look like, well, it does actually look like what we want. It's just not perfect because our camera isn't following the player, so it definitely doesn't have a right feel. But we see that as I hit W and S, things get moved along appropriately, as well as you can see the basics of my mouse movement indeed affecting the player's rotation in the way I want it to.
There you go.
However,
so now, how do we go about locking the camera to it?
All right, so to do the camera, I'm going to do, wow, just kind of chilling in space.
We're listing.
The way I want the camera to work is I don't want to just attach the camera right behind the player. I want to actually have the camera sort of try to catch up to the player, which means that we're going to have to interpolate between the target rotation of the camera as well as the target position of the camera as the player is moving. So we're going to perform some interpolation. We're not just going to immediately constrain ourselves to the back of the player, because that would look rather unrealistic. We want to have it follow along to some degree.
Yeah, this way it'll look more like you're actually following behind the ship and adjusting after it adjusts.
Exactly. So if we jump into our player camera, the calculations for this are actually fairly straightforward. We need a couple public properties. One is going to be the movement dampening. And then the other is going to be the rotation dampening. And again, by modifying these variables, you significantly change the feel of the game, which is why I set them as properties that can be modified and not as constants or not as hard coding them. Now the movement dampening is going to be set to 8, and the rotation dampening is going to be set to 0.5f. Again, I have to add the f because in C#, 0.5 is a double literal, not a float literal. Adding the f turns it into a float literal. Now our update method is simply going to say var position. So the position of the camera is going to be player transform point 0.5f -5. So what does this mean? Well, we're going to retrieve out a point that is above the player by 0.5 units and behind the player by -5. The transform point does its translation relative to the player's transform itself, so we don't have to worry about its rotation, which is nice.
Alrighty.
Then I'm going to say camera.transform.position equals vector3.lerp between camera transform position followed by the target position with time.delta time multiplied by movement dampening. So we're just interpolating between the target position and the current position of the camera. The rotation is going to be done in much the same way. The rotation is going to be set to quaternion.look rotation. Then I'm going to pass in the forward vector as player.transform.position minus camera transform position with the up vector of player transform up. So this will actually look towards the player because we're passing in the forward vector as the player's transform position subtracted by the camera transform position. So we're looking at the player, and then we consider it to be we consider the up direction of the camera to be the same up direction as the player. Then all we need to do is say camera.transform.rotation equals quaternion lerp between our current rotation, which is going to be I'm going to do slerp, from our player's transform, camera transform rotation to our target rotation, and it's going to be modified by time.delta time multiplied by rotation dampening. Now I'm going to come back into Unity and see what happens. We have a tiny problem.
Yeah, it's doing what it's supposed to do, but it's doing it too much.
Kind of. We actually need to lerp between our player's transform rotation, that current rotation, to our rotation. And that should give us the effect. There we go.
Much sexier.
Yep. Okay, so now we have a very basic player controller in place that allows us to move the player based off the position of our mouse. And I can use W and S to make it go either faster or slower. Okay, so the next thing I'm going to go ahead and do is there's actually some stuff missing out of our player controller that I wanted to add in, such as rotating, applying our afterburner, and strafing. And those are things I just sort of left out while we were working on the first iteration of our player controller. So the first thing I need to do is I need to add in a couple more variables. The first one I'm going to add in is my afterburner modifier. Our afterburner modifier will modify the velocity of our player if he has the afterburner enabled. The next thing I need is a public float strafe modifier. The strafe modifier is the amount of give that will be applied to our player along the x-axis as you hold down either the A or the D keys. Now I'm going to set these up with some straightforward defaults. The afterburner modifier is going to add 50 units per second to our speed in the z-axis, and our strafe modifier is going to apply a maximum of 7 units per second in the x-axis.
Alrighty.
So now that we have those two bits of data, I can come back down here to our update position, and I can play around with these values. Now, what I'm going to do here is I'm going to say, after we calculate our variable velocity, I'm going to say, after we calculate our target velocity, I'm going to modify the target velocity based off whether the input.getKey keycode.tab returns true. So if they're pressing tab, I want to add to our target velocity our afterburner modifier.
That makes sense.
All right, so that's our afterburner. Next up, we need to do our strafing. Our strafing is going to be done in our translate call, where I'm simply going to say input get axis horizontal times time.delta times strafe modifier. So that this will allow our player to move left and right depending on if you are hitting the A or the D keys. Sound good?
Alrighty.
Okay, the last thing that we're going to do is implement rotation. Rotation is going to be handled in the update rotation method. I'm simply going to say if input.getKey E player transform rotate 0, 0, negative 90 F times time.delta time. So this will roll him to the right. Then I'm going to say if input get key Q, then player transform rotate 0, 0, 90 F times time.delta time. And that will rotate him to the left. So I'll see if those worked.
Alrighty.
Jumping back into the game, if I go ahead and hit tab, you see that we did indeed accelerate, and if I let go of tab, we decelerate. And the rate at which we decelerate and accelerate are based off of our velocity dampening. Next up, we can indeed strafe by hitting the A or the other key, and then we can rotate by hitting E or Q. Sound good?
Yeah, that's pretty cool.
Okay, so that pretty much wraps up our player controller and our player camera for now, but let's take a step back and talk about the relative positioning versus absolute positioning. So if I set use relative movement to true, what we'll see here is our cursor should be constrained in the center of the screen. Whoops. I don't know if you guys saw that, but it just messed up. So now, I'll show you guys again in a second, but now, so you see that right now I can still move, but my mouse cursor is no longer visible. That's because my mouse cursor is hidden and locked in the center of the screen. And now I can change the sensitivity of the movement by modifying the mouse sensitivity property on my player controller, which is really cool, and it's a very nice effect to have when you're using a standalone player. That being said, half the time that you use there you saw it. Half the time when you're using the editor and in combination with lock cursor, the mouse cursor will decide to jump up all the way onto the pause button. I don't know why, but it does.
Well, that eliminates that question.
Which means when you click, so okay, now I think I'm in there for good now, because it usually only happens once and then it doesn't do it again. But let's try this again. So I'm in here and I click and boom, I'm paused. So I have to actually like click in. Nope, it did it again. It is incredibly frustrating. and very annoying, and makes working with with this particular controller inside of editor mode very difficult. As a result, that's why I have a Boolean flag that I can set to true or false, whether or not I'm in the editor or I want absolute positioning versus relative positioning. Because as you see here, it's a lot smoother and it doesn't accidentally hit the pause button all the time.
So you will change that to true for the final build?
Yes. Or
Okay,
perhaps even
gotcha.
leave it as an option for the user himself. Depends on on what the user wants. I think that leaving it as an option to the user might be a good idea too, which is why it's not a constant or a define. It's an actual property that can be changed.
Cool.
Okay, so
Oh, I didn't know it did that. That is really annoying.
yeah, I got just the first implementation of this that I did, I used the absolute positioning, but then I found that I really wanted to change the sensitivity of the mouse, which I couldn't do with absolute positioning, so I did the relative positioning, but then I got so fed up with the editor completely breaking that I just turned it into a flag that we can turn on and off.
There you go.
But anyway, now we have a player, and he can move around the world, and he can have the afterburner, he can rotate left or right, and he can strafe left or right. So that's
Very
really
nice.
cool. So I think that pretty much wraps up what we want to do with the player controller in this video. So yeah, stuff and things.
All right. That was exciting. Let's move on.
Awesome.